This is my video on matrices and their operations. I'm going to try to move as quickly as possible. Find the additive inverse of matrix A, then add matrix A and the inverse to get the additive identity. So we know that the additive identity matrix looks like a 2 by 2 matrix with zeros as each of its components, A, B, C, and D, which makes sense because we know that our additive inverse, when we're doing operations of numbers and variables, that our additive inverse is always 0. So it's just a matrix full of our additive inverse. So in order to create our additive inverse, we are just going to create a new matrix, new 2 by 2 matrix that has the inverses of the original components of matrix A. So the inverse of positive 2 is negative 2, the inverse of positive 4 is negative 4, and so on and so forth. So this would be our additive inverse. And then we will prove that this is our additive inverse by adding these two together, and we should get our additive identity. So in order to add matrices, oh god, that's gonna get me. I'm gonna create another 2 by 2 matrix. Okay, and you're just going to add each of these components together. So positive 2 plus negative 2 gives us 0. Positive 4 plus negative 4 gives us 0. 1 plus negative 1 gives us 0, and 7 plus negative 7 gives us 0. So as you can see, we did end up getting our identity matrix, okay? And similar concept with our multiplicative identity. So here we're going to find the multiplicative inverse of matrix B, then multiply matrix B and its inverse to get the multiplicative identity. Similar concept, a lot more steps. So the formula that you see at the top for the inverse of B is how we would find the inverse of B. So the first thing that I'm going to do is find my determinant of B so I can plug that into our equation for our inverse. So the determinant of B, as we should recall, okay, the determinant of B is going to be A times C minus ABC, right? B times D, yeah. I had to remembering that off the top of my head. So, A times B, here we would get 2 times negative 1 minus negative 1 times 3, and we would end up with 1. So here our identity matrix would be 1 over 1 times, and then if we plug in the different values for this formula, we would end up with negative 1, 1, negative 3, and 2. Okay, and just because we're multiplying this whole matrix by 1, we can go ahead and we know that that just creates a 1 pair and doesn't add value. So we can just this now is our multiplicative identity, and to prove that it's our multiplicative identity, we're going to go ahead and multiply our original matrix B by it, and we should get our it's our multiplicative inverse, and we should get our multiplicative identity back. 1, negative 3, and 2. And just also as a reminder, our multiplicative identity, okay, our multiplicative identity is this matrix 1, 0, 0, 1. Okay, so that's ultimately what we are looking to achieve once we do this multiplication up here. All right, so when we multiply matrices, it's a little bit different than adding. Okay, we're going to be multiplying rows and columns using addition. So here, in order to find our first number that's going to go here in our matrix, we're going to look at our first row and our first column. Okay, we're going to multiply each of the components. So that'll be 2 times negative 1 plus negative 1 times negative 3. And that will ultimately give us, well, 2 times negative 1 is negative 2 plus positive 3. Well, that'll give us a 1. So far, so good. And I'll go ahead and do one more, and then obviously it'll make more sense. So for example, to get this number in the upper right hand corner, okay, we would again we would look at multiplication and addition using our top row and our right hand column this time. Okay, and that would be 2 times 1 plus negative 1 times 2, which will give us 2 plus negative 2, which is 0. Okay, and if we were to continue this pattern, we would see that we would get our identity matrix if you did that for each of the numbers in each row, each column, multiplying the components and then adding them. We would ultimately get our identity matrix. And just for the sake of time, I will move on to the last two steps of this problem. Here we want to add our, we're going to be adding matrix A and B together to see if they're commutative, and then on the next slide we're going to be multiplying them to see if they're commutative using multiplication. So here, again, with addition, you're just adding each of the different components. So here we would end up with a matrix that is has 2 plus 2, and then we would have 4 plus negative 1. We would have 1 plus 3, and we would have 7 plus negative 1. So our matrix, or the sum of matrix A and B, would ultimately be 4, 3, 4, 6. And if we did the same thing on B plus A, we would get 2 plus 2, negative 1 plus 4, 3 plus 1, and negative 1 plus 7. And again, we would end up with the matrix 4, 3, 4, 6. So our matrices commutative using are under addition. Commutative, well, yes, they are, right? We just proved it because we got the same matrix using addition either way. So now let's explore if matrices are commutative under subtraction using this example. So again, we would, in order to multiply matrices, we would look at each row and each column and add them. So if we were to multiply A times B, for our first number, we would get 2 times 2, which is 4, plus 4 times negative 1, which is negative 4. I'm sorry, that's wrong. Let me go back. I should be looking at each row and column, so I should circle them. I always circle them. So 2 times 2, which is 4, plus 4 times 3, which is 12. And for our second part, let's do this bottom number in the bottom right. That would be, let's do it in a different color, sorry. I'm running out of time. So let's do these two. So 1 times negative 1 would give us negative 1, plus 7 times negative 1 would give us negative 7. And just checking my answers to make sure that's right. Yep. So ultimately, when we fill in all of those steps, we would end up with the matrix 16, negative 6, 23, and negative 8. And then for the second matrix, B times A, using those same steps, if you were to do them using all of those wonderful steps that I don't have time for, we would end up with 3, 1, 5, and 5 matrix. So here we ended up with two different matrices once we multiplied them in a different order. So is our matrices commutative under multiplication? Well, no, they're not commutative. No. Okay, so they are under addition, but they are not under multiplication.